presentation here. Now, so Ed sort of brought the chaotic dynamics into actually mission designs. The first thing was saving a Japanese mission to bring something around the moon after they had some disasters on the way to achieve this. And yeah, so I always enjoyed talking with him about this kind of problems. And now it looks like there is an opportunity to bring some, as I said before, recent developments in symplectic geometry together with some maybe even more interesting mission designs by using certain structures which haven't been used before. Okay, Ed.
Yeah. Make sure I got all this to work right here. It works, yeah. Okay. So this is an applied talk as opposed to the one by Urs. And I have it two parts. The first part of the talk will be more or less a very applied introduction and so sort of a motivation of some of this work from real examples that have been used in practice. And the second part of the talk will be some recent results on some of the mathematical aspects of what I'll be talking about. So this is the plan here. First I'll give a motivation and historical perspective. And then I'll talk about capture and the weak stability boundary, both from a very, very heuristic point of view with some applications. And start to get into a little bit of the dynamical systems of this with some recent work of Garcia and Gomez in 2007. And then I'll end with talking about some new work I just published a few months ago with Marian Gidea, Francesco Topputo on the manifold structure of these things we call weak stability boundaries. So, like I say, it's be very applied. There's no contact structures here or anything like that. So let's look at a very applied problem of trying to get you can view P1 as, like, for example, the Earth. P2 could, for example, be the Moon. Any masses you want, but we'll work with those two. During this talk, I'll probably pretty much focus on those being those kind of examples. And then you start out with a circular orbit about the Earth, and you'd like to end up in some elliptical orbit about the Moon. And typically the way this works is at some point in this orbit, you hit it with a delta V. Delta V is a change of velocity which brings you out of the circular orbit. And then you coast to the Moon. And then here, typically using the Hohmann approach, which is using patch conics, which I'll mention in a second, you usually, using the patch conics, you come in here with quite a high velocity, and you have to do a large delta V to slow down. So the Hohmann transfer, basically, this was done in the 20s. German guy, engineer.
Delta V means fuel.
Delta V means fuel, yes. It's actually change of velocity, but through a quantity an engineers know well called the rocket equation, it translates into fuel. And the delta V is like in velocity units per time. And the rocket equation, by using the characteristics of the engine, translates this into kilograms of a particular type of fuel you might be using. And this is so typically to leave the Earth at reasonably high altitudes, say a couple hundred kilometers up, you need about 3 kilometers a second to leave. And usually when you come in to around 100 kilometers here, altitude, usually you're coming in at about 1 kilometer a second. So if you want to go into orbit, you have to kill somehow 1 kilometer per second. And that's the applied part of this talk. That's what motivated me years ago, in 1986, as a matter of fact, when I was working at the Jet Propulsion Lab. And typically, prior to that time, the way these routes of the Moon were found is you view this as a decoupled two-body problems. You forget about the Moon, you have a two-body problem between your spacecraft and the Earth, and that's going to give you one Hamiltonian, and then when you arrive at the Moon, you have another Hamiltonian and between the spacecraft and the Moon, and then what you want to do is you want to minimize the energy of both those Hamiltonians under all possible paths to the Moon, and what you end up getting is conic sections, like an ellipse. But then you have this problem here of a large overflight velocity. DVC, the delta V of capture, and it's quite, like I mentioned, quite large. So I got interested in this because being a mathematician, the first thing I noticed was, well, why can't you make this 0? Why does it have to be at 1 kilometer per second? Because, you know, basically, how can you do this so you drift in and automatically get captured for nothing? And it's called ballistic capture, and prior to this time it didn't exist. So the reaction I got was you simply can't do it, unless perhaps you took 100 years to get to the moon, then by doing some fancy gymnastics with the trajectory you could somehow float in and get captured. But I knew from the work of Alexeyev and Sitnikov and Charlie Conley that you did have, for example, in the Sitnikov problem, ways you can get permanent capture to occur by the transverse intersection of various hyperbolic manifolds. So I realized that, well, if you can get permanent capture to exist for that problem, there's a chance that you could get ballistic capture to occur. And the solution was obtained. Basically, what you'd like to do, so how do you solve this problem of ballistic capture? What you'd like to do is basically arrive at P2, which is the moon, with negative Kepler energy with respect to that object. So you have your Kepler energy function, which is 1/2 the velocity squared minus 1 over the distance to the moon. You simply want this to be negative. And you want the capture to be temporary, because if it was permanent, in backwards time you couldn't get out to get there in forwards time. So you want to have it temporary. And basically what you're looking for is a capture between, it's a capture actually which is a transition between capture and escape. And from dynamical ideas, one realized right off the bat that's going to be a very delicate thing, quite unstable. And it was found by, number one, estimate a region where it occurs, which we call this weak stability bound 86. And the second is you find a trajectory from where you're starting, near where you're starting, P1 to near the moon, to get there. And this was solved by the method of backwards integration. So basically the idea is, once you find this capture region around the moon where ballistic capture can occur, you do a backwards integration from it and see where you have to come from to get there. And you can actually solve the problem of ballistic capture of the moon using this. However, it's very crude, and but it works. How do you find this weak stability boundary region? Well, I'm going to come back to this algorithm shortly, but right now let's start out with a really crude algorithm. This is the one I came up with in '86, and it's pretty simple. This is how you estimate where this region is. Pick a radial line and an angle theta, the line's L of theta, and basically you notice that here's P2 is the moon, here's the Earth over here, and you notice that this is a game you play. You propagate all these trajectories, assuming a fixed eccentricity between 0 and 1 relative to the moon, and you assume that your velocity vectors are all normal to the line. So sufficiently close to the moon, everything comes back nearly to where you start, and you know this must be the case, at least in the plane of circular restricted problem by a theorem due to Martin Kummer. You have a KM structure there, and you know everything has to be quasi-periodic. However, as you move out sufficiently far, you find on the computer that once you start, it doesn't even go around the moon, it goes over here. So stability is defined in the following way. Stability means we do one cycle about P2 and return to L with negative Kepler energy without first having gone around P1. Everything else is unstable. So what you do is you iterate between stable and instability, and you find there's a critical distance depending on the eccentricity and the angle where this occurs. And when I did this back in '86, I just found this one distance here. Now, this recent work I'll mention shortly, this is a much more complicated thing, but at this time I found this one distance given these parameters. So the weak stability boundary is defined by the locus of these as E varies in 0, 1 and theta between 0 and 2 pi. And then what you do is you pick a point in here, you do a backwards integration from it, and you can adjust your parameters in here and tweak them so in backwards time you start at the Earth sufficiently close. Now, there's a problem with this. You can't get too close to the Earth if you're working with a three-body problem because there's a family of invariant tori going around the Earth. But you can get fairly close, and for the purposes of the application, that was good enough. Fairly close means about 60,000 kilometers. What you end up getting for this mission I worked on is this picture here. What you have is you have and for this particular design, this was produced in '86. It was a study done at JPL called the Lunar Getaway Special, and it's actually the first ballistic capture transfer, I believe, ever constructed. And it uses solar electric engines, little tiny ion engines that spew out atoms. And the thrust is like the dime in the palm of your hand, so it takes a long time to spiral out with these after you release it in Earth orbit. There's about 3,000 spirals here. It takes about 2 years to reach this point, which is right beyond the invariant tori. Then what you do is you shut your engines off, and this is your ballistic capture transfer. You coast, and you go over in here, and you stop here. And this turns out to be a point in your weak stability boundary. Then where you capture with negative Kepler energy, you turn your engines on, you spiral down, and this solved the problem. Now, the problem with this approach is it worked, and actually this was used by the Europeans. This particular design, although it was not viewed as practical at NASA because it took so long to get to the moon, it was used by the Europeans in '04, so it did see the light of day eventually. With this approach here, by doing this backwards integration, like I say, you can't get sufficiently close to the Earth, so it was desired, you want to do two things. Is there a way to leave at any distance from the Earth and go to any distance to the moon where you're ballistically captured? And that actually goes back to a mathematician, Charlie Connelly, who conjectured this back in the '60s. Is that possible? This was close to it, but not quite, because you can't get arbitrarily close here, but you could actually, if I wanted to start down here, this could have been done. So you can get arbitrarily close here, but not here. So this almost solved this conjecture, but not quite. This is for a three-dimensional problem, as you can see, and these would be three-dimensional Hills regions, which I'll talk about shortly. So what you'd like to do is search for more useful transfer, and this didn't happen until January 1990. I was under some encouragement. I was leaving where I was employed at the time, and I heard about this mission to the moon that Japan had wanted. It was a failed mission. I don't want to go into the story here too much, but basically they had launched 2 spacecraft in Earth orbit, a larger one about the size of a desk and a smaller one about the size of a grapefruit, and the small one went off to the moon on a Hohmann transfer and never made it, as far as they knew. So they wanted to bail the mission out and get the larger one there, but it had no fuel. So out of desperation, as I was leaving my job, they asked me how to do it, and I could have cared less at the time, but for some reason I saw how to do this, and it's described in the book Fly Me to the Moon. A much better description, actually, was in Helmut Hofer's IAS lecture last year. He did a wonderful job describing this, and in fact, it was like he was there. It was scary, actually. I said, was he there? So what you end up getting is the observations of how to do this is you have to work with a 4-body problem to make this work. This does solve the Connelly conjecture. This is one of those results that was unnoticed in the math community, unfortunately, until recent years, but it did solve the problem. And the way you do it is you have to break up, look at 2 weak stability boundaries by this algorithm. And basically what you have is a boundary here due to the Earth-Sun interaction, which is roughly 4 times the Earth-Moon distance. And what you do is your trajectory is designed to go out to this boundary where it moves in a very complicated way here because this is between capture and escape. And then it falls back to here. And as it's falling, the sun is pulling on it. And it falls down to another weak stability boundary here where it gets captured ballistically. The way we found this was, again, by backwards integration. We started here where we wanted to go, went in backwards time. And here you can leave at any distance you want. So this is what it really looks like. And this was the spacecraft. Basically, the way, I'm not going to go into this here, but basically what you have is invariant manifolds, which are topologically cylinders which leave the Earth. The trajectory more or less follows these out to here. Then once it loops down, it finds another set of invariant manifolds leading you down to here. And if you look at the big picture, this is what this looks like. The trajectory goes out more or less to this Lagrange point region, but it can go on the opposite side where there is no Lagrange point. But there's a reason why this is happening, and this will be later on in my talk. And it loops down over to here. This is in a fixed coordinate system. That's why you see this loop. And I'll be talking about this. What's really going on in the capture process is the trajectory comes in, and this is this is a Hills region where the particle can move around the Earth, and it opens here around the Moon. Urs talked about this in his talk about how you have these different regions. I'll get into this shortly. But in any event, you have unstable periodic orbits here called Lyapunov orbits, and they have stable and unstable manifolds. And at the time we did this, we realized what was probably going on was that they intersected somehow, and somehow you had a very complicated region where somehow the trajectory would come in and get ballistically captured, although we had no clue how this was happening. I knew it would probably be possible to ever understand this, so this is about as far as I got, was drawing this picture back in 1994. However, years later, it turns out this actually is making some headway with this. I just want to mention, since Helmut showed a very cool-looking spacecraft picture in his talk of last year, that I had to put one in too. So this is there's actually going to be a mission to the Moon by NASA in later this year, early next year, and it is going to use the same transfer. And it's called the Grail mission, and they're going to be sending 2 spacecraft to the Moon, and they're going to be going on opposite sides, and they're going to be measuring the interior of the lunar structure. So this will luckily be used again, which is very nice. The first paper, by the way, published on the dynamical mechanism of this capture transfer was actually, I had published it in '94 as a Barcelona, a Center of Research Math at the Autonomous University of Barcelona. And then independently it was ascribed by Jerry Marsden and his group at Caltech in 2000. I just want to mention that in an effort to understand the chaotic structure associated with ballistic capture, it can be done analytically by looking at energies which are parabolic, where the orbits actually will go to the Moon but actually extend out to near infinity. And if you look at parabolic type orbits, which go to ballistic capture at the Moon, and the 3-body problem would be Earth, Moon, and then a parabolic trajectory, and you look at that trajectory coming into the Moon for capture, you can study it in terms of the family of parabolic orbits, and the fact that these orbits exist on topological cylinders for 0 perturbation. As soon as you perturb them, these cylinders break and you get a homoclinic behavior, and the homoclinic behavior can be shown to be associated with ballistic capture. I'm not going to do any of that here. These energies are way out of the area which are of interest for, I think, for most of the problems that I'll be discussing. However, in this book here, Capture Dynamics and Chaotic Motion Celestial Mechanics, which was published in '04, I do have a proof of this in here. And basically, the whole book leads to a proof of this. We are interested, however, in lower energies for non-parabolic motion, and that's what I'm going to be getting into. I just want to mention before I get into that, there are other applications of the weak stability boundary that go beyond spacecraft motions. This is one that I wrote a paper with a colleague at Princeton, Richard Gott. It's on the origin of the Moon. We published it in the Astronomical Journal in '05, and in this case, you look at the weak stability boundary around L4 and L5 points, which are stable points, and this has gotten a lot of attention in the astronomy community. I'm now working on the final stages of transfer of solid material between planetary systems with Renu Malhotra and Maura Martin. It's an AstroPH paper right here, and then with Franz Pretorius, who's here, we started beginning discussions on possible use of these techniques for merging of black holes. We haven't done anything with it yet, but it seems like it might be possible. So this would be another unexpected application of this work. So now I'll get a little bit more mathematical, and we look at the restricted 3-body problem. This was defined in the previous talk, and basically this is a little bit opposite to what Urs had described. He had the Moon over here and L3 over here, so I reversed it. However, later in my talk it goes back to the way you had it. So here the difference, this is in the plane. You've seen these equations before. I'm not going to go into this more because he did a thorough job describing them. And associated with the Jacobi energies, you have a Jacobi energy function which was defined, and I'll be referencing that later. But as the energy changes, the motion of the particle at first is restricted to either one of these two masses. As you slightly, in my case, decrease the energy, because I have a minus sign in front of it, where he increased it. As you slightly decrease it, where the particle is more energetic, then the Hills region opens up. The Hills region here is outside in these three components. Here it opens up, and you have a family of periodic orbits of these Lyapunov orbits, and the particle can pass between. If you decrease it further, this side opens up here. When this first opens up, you have a Lagrange point here, L1. When it opens here, there's a Lagrange point here, L2. And then as you keep going, it gets shrinks until eventually it moves the entire plane. Now it's reversed the way it was before. Here's the moon here, and the Earth is over here somewhere. And so here's your Hills region on this side. And here you've opened up here where the neck is, the neck region. And here is your Lyapunov orbit, which goes in this direction. It's unstable. And these are stable manifolds leading to it here and leading to it here. And these move away. These are unstable manifolds. And I'll be making good use of these later. So Conley had determined the dynamics locally near these Lyapunov orbits in a very nice paper he wrote in 1963. As I mentioned here, he conjectured in that paper that you could go globally, go forwards and backwards from the neck and get a transfer from near the Earth to near the moon. And as I mentioned, that was solved by this 1991 transfer. I'll be coming back to Conley's work shortly. This is basically, if you project these manifolds down, what you see here is that if you want to go from the Earth region to the moon region, you have to go on the interior of the tubes, these topological cylinders. That's the only way you can reach to go between the regions. So these are separatrices of the energy level. And if you start over in here, you'll do a certain number of cycles about P2, the moon, before you finally go in here. I'll be talking about that later on in my lecture.
You have this narrow band on top of the tube and below where it's sort of empty.
What band is
So between the gray region and the top cylinder, say, there's this narrow region in between still. It's still white.
That should be infinitely close.
I see. Okay.
Yes. Sorry, that was it's a graphic. That was a very good point. Yeah, they can't sneak through there.
Right, exactly.
Yeah, they go, oops, how'd they get over there? Okay, so the real breakthrough with this came, as I mentioned at the beginning of my talk, that we had no idea of what was going on with this ballistic capture, and we knew that this weak stability boundary, that the way I defined it was really just the tip of the iceberg. And I gave up on it, but Garcia and Gomez was a student of Carlos Simo, and he wrote this wonderful paper in 07 called A Note on the Weak Stability Boundary, and there he generalized the algorithm. And this has made all the difference in the world. By the way, I want to mention why this region is so hard to study. First of all, it is not an invariant region. And number two, it does not exist at any energy level. It varies. At different points in the boundary vary according to Jacobi energy, and it's not invariant, so it's tough to study this. So what he did is he proposed to look at the previous algorithm and generalize it not to one cycle, but you look at the change in stability from n cycles. And you talk about the nth weak stability boundary. And the following figures I obtained were joint work with Francesco Topputo and Marianne Gidea. But Francesco, I have to say, is the guy who is wonderful with the computer. I mean, he's done some remarkable computer work for us. And he's done pretty much all the computer work I'll be showing. But here is the same picture as before, but now we're going to be looking at n cycles about here, and then you look at the change in stability as we did before. And here we go. It's the same picture. I don't know what happened here. It's n stable if you make n terms about this thing and return with stability where the Kepler energy is positive. And you have to come back to the section, intersect transversally. Otherwise, it's unstable. And this is what ends up happening. You don't get one point where it transitions. You get infinitely many. You get a countable set, actually. And what you end up getting is sequences. This is what ends up happening. you end up getting the blues are the stable points. Suddenly, and these are unstable, here's your first transition. But then you notice there's another transition. And what you end up getting is, for these stable regions, you end up getting a countable union of intervals whose endpoints are these transitions, and it's a countable union of open intervals. And of course, the boundaries of this is the weak stability boundary, which is therefore a countable set of points, which has a Cantor-like structure. So what we get here is this is the open stable region. You take the union over all the this is the nth stable region, and you take the union over all theta and eccentricity in here for all of these, and it's still an open set. And the weak stability boundary of order n is then the boundary of that. So it's a locus of all points r star along the line for which is the change of stability from the initial trajectory. And as I mentioned, you can write it as a finite set of points. I mean, a countable set of points. I just want to say, computing this boundary is.
How many of these things you usually compute these points for practical application?
How high do you go with the n?
Yeah, well, or I mean, this weak stability boundary is a countable set of points. So just you practically.
That's a good question. I don't know how. You'll see the pictures in a moment. There's many thousands, many thousands of those. Actually, for a fixed E, you need to do 360,000 integrations to compute Wn for each n, and in that is a complicated set where you have many gaps. This is what the stable set looks like for equal to 0 for W1. This is just for one cycle only. Here is what happens to this for 0.4, 0.95. Here's the boundary. Here's the weak stability boundary. Here's the red. The blue is the stable region. And if you want to compare these sets, this is joint work I did with Francesco Topputo. We actually did it we compared the set for the moon, which we've just done here, to the Jupiter case. So it's 0.012 for the moon and 0.001 mass ratio for the Jupiter case. And this is what you get. The one on the right here is the lunar case, is the Jupiter case, a bit more complicated. These are for the eccentricities being 0.2. If you blow this up, you see a very interesting structure.
Would you expect that these sets which lie in the Q space, in position space, so they should be related to intersections of pieces of these tubes in the stable unstable manifold in phase space?
I'm going to get into this, the next part of the talk. That's exactly what I'll be talking about. As you can see here, this is how the Jacobi energy varies along a weak stability boundary. The values go from, what is this, around 1 up to 3. So there's a huge variation. Now, the first part of my talk ends here. And what I'm going to get into next is the manifold structure, exactly what Helmut was asking about. And this was just published in the Science Journal of Applied Dynamical Systems. And the main result is this. The points on the stable manifolds of the Lyapunov orbits about L1 and L2 are contained within the weak stability boundary, provided the points satisfy the zero radial velocity condition, r dot equal to 0, and the negative Kepler energy with respect to the moon, or P2. And this is done for a range of the Jacobi energy. So in other words, if you look at the stable manifolds, Lyapunov orbits, and you look at those manifolds where r dot's equal to 0 and the Kepler energy is negative, those lie in the weak stability boundary, which is, I think, a pretty amazing result. So next slide.
And can you say something with the number n? How often you go around? Does it something to do with the number of I mean, you have this in the phase space. You have these tubes going sort of around.
Is this okay?
Perfect.
Okay. Yes. Sorry.
So in some sense, you could think of these tubes from the Lyapunov orbit going around for a while and then intersecting the stuff. So
It's exactly what happens.
the n is depending on something like this.
Yes, exactly what happens. You you make use of the separatrix. In a nutshell, you have the tubes of the manifolds winding around. And if you're on the interior of the tube, those give the points which can pass to the other side. Those will be the unstable points. Those which are on the exterior of the tube, they'll stay in the P2 region to a certain number of cycles. Those on the tube will cycle around a certain number of times, and those will be the weak stability boundary points. So the separatrix property of the tubes together with the cycling is an exact analogy to the way we define the weak stability boundary to begin with. Okay, so what I'm going to do is start here. This is the Jacobi integral. See, what do we leave out? This is the Jacobi integral that was in the previous talk. But what I'm going to do here is go to, let's see, where are we here? Okay, so I'm going to be starting here. Okay, so the L1 point is a center saddle point between the neck. And we have a, let's see, the Lyapunov. Okay, now the notation here is a little bit different. T represents a Lyapunov orbit, and T1 and T2 are the Lyapunov orbits around L1 and L2. So basically for each Jacobi energy, you're going to have a Lyapunov orbit, which is in the neck here, and they will have a two-dimensional stable and stable manifolds. Here we have them labeled as so, which are topologically cylinders. And as I mentioned, these are separatrices of the energy manifold. And I described this result very briefly. So the trajectories which lie in here outside these tubes will wind around a certain number of times before entering a tube and going on the other side. And those on the tube will asymptotically head towards Lyapunov orbit. Okay, so I'm going to discuss this more now. Okay, so let's make it. This is how we're going to be defining cuts of the stable and stable manifold. The ith cut of the stable manifold is the way we're defining this is the set of all points where the manifold cuts a surface of section, two-dimensional surface of section, with the property that the points on the cut for the stable manifold will do I cycles around P2 before heading towards Lyapunov orbit. Okay, that's how we define the ith cut of the stable manifold. And the unstable manifold is the same definition of backwards time. It is found that when the stable and unstable manifolds intersect transversely, the topological circles are destroyed, and you get a finite circle, a finite collection of broken circles. This is a result of Marian Gidea and Mastamont in 07. And as I was saying, even after circles are destroyed, the broken circles maintain the separatrix property. So, for example,
what do you mean by that? So I can imagine, so if you have this surface, so the tube comes through, then maybe I get the other one, the unstable one comes through, and then you have these two circles intersecting, and then depending which part of the region I am, certain things will happen in the future.
Well, for example, here's an example of what happens. When the W1 stable intersects the fifth iterate of the unstable, then the W6 of the stable actually breaks and will wrap around this one here. So in the interior, you can define, again, the separatrix property. Okay. All right. Now the Gomez and Garcia and Gomez conjectured the result that we are investigating in more detail, and their conjecture was that for some range of the Jacobi constant C, the nth weak stability boundary is contained within the closure of the stable manifolds about L1 and L2. And what we'd like to do here is provide a geometric argument for this and investigate it in more detail.
So the energy we are dealing with is above, so we pass two Lagrange points. So there's a picture where it's open.
Yes, basically the range of energies we're dealing with is right when the neck starts to open, all the way to when the other side opens, and a little bit beyond that.
So yeah, it opens at a small body and it's open between the two bodies.
Yes, and that full range we have this. In fact, when it opens for both of them, you can still go further down where it actually opens up wide. And we call that value C min. Remember, as the Jacobi energy decreases, the energy is actually the velocity of the particle increases. So the far Lagrange point is where we're calling that. There's so many notations here. Would be that'd be L2 would be the far one, the exterior Lagrange point, and the Jacobi constant for that is C2. So for the Jacobi values less than C2, that's going to be open, and we take those down to a value C min, and C min is substantially lower than C2. All right, so we need we're going to be making some topological assumptions in order to prove something about this. And these are the assumptions that we're making on the invariant manifolds. And it turns out, under numerical work, these are satisfied for these sets of energies, actually. The trajectories on the branch here, now this is T1 is the neck between the two Hills regions. So the trajectories on the branch of T1 in the P2 region, this is the region about the moon, the smaller region. Should I draw this on the board, or is this pretty clear?
Okay, so if you take this tube coming from this thing in between the two
Yes.
regions, then and you project it down, it would go
n times around the moon. Right, that's correct, about P2. So we make this one assumption on that. On the other hand, if you take now the trajectories on the branch of the unstable manifold.
So this is for which, I mean, this presumably depends on the mu or what? You have to be.
This is mu sufficiently small. Actually, this works for a range of mu, but we're just fixing mu small here.
P2 is the bigger?
P2 is a smaller one. So P2 is a smaller one. And if you look at the branch in the P2 region, we're assuming that it makes n turns around P2. If you look at the branch in the P1 region, it makes at least one turn about that. That's the larger one. And now if you look at the, this is now the Lagrange point on the far edge. We assume that in the P2 region it makes at least n turns about P2, and in the outer exterior region it makes at least one turn about P1 on the exterior. So these are our topological assumptions.
And at least one.
At least one, yes.
You don't care how big it is.
No, at least one.
But then he cares that there is an example for this. But you say numerically one can show for small, so given n and so on for this body for mu sufficiently small, that's has been numerically.
Oh yes, we have many cases here. In fact, this works for a wide range of mu. And right now for these simulations, we're assuming mu is, I think, 0.01, but it works for many cases that we looked at. By the way, this is called hypothesis A. These conditions on the stable and unstable manifolds. However, there are trajectories which don't satisfy this. It turns out that what this is here, this is your weak stability boundary region in here, and this is the projection of your energy surface onto the plane with the property that all the points in here have a Jacobi energy which is within our bounds. In other words, the Jacobi energy does not go below the C min. It turns out that if you're close to C min value out here, a number of the points will have the property that they will actually collide with here. They will not cycle around here, but they actually head towards collision. And these are not in this hypothesis, and we call these points of type B. And one of our projects is now working with these. We're trying to understand the set better. Okay, so this is the main result that we have. By this notation here, this is the nth weak stability boundary such that the manifolds satisfy condition A, hypothesis A. And these are the complement type B I mentioned that don't satisfy it. And this is just a surface of section. This is going to be a surface of section through P2 at angle theta with respect to P1, P2. Again, P2 is a smaller one. So these are the n minus first cuts of the manifolds with the section. Then our main result is this. The nth weak stability boundary can be written as the union of the stable manifolds of T1 and T2 of the n minus first cut. such that r dot equals 0 and H2 is less than 0. H2 is the energy with respect to P2. So negative Kepler energy and r dot equal to 0, these are basically what this boils down to is that the union of the weak stability boundary of satisfying the hypothesis A is really equal to the union of the stable manifolds of T1 and T2, subject to these conditions. Now these are examples, by the way, of what happens when you propagate trajectories from the weak stability boundary, showing that they do lie in the invariant manifolds. You can see them heading towards the Lyapunov orbits. Here's the boundary here. You pick a point here. In this case, you'll see it go over here. If you pick a point here, etc. You just pick different points showing how this works. C1 is the neck point between P1 and P2, and you're taking energies greater than that, which means that you now have 3 Hills regions. They're not overlapping.
But he has a minus sign in this.
I have a minus sign, yes. In this case, all trajectories are n-stable for any n about P2. And the Kepler energy is always negative inside the P2 region. And when you do this analysis, what you have to do here is just you have to be aware of what the energies are for both H2 and the Jacobi energy to make sure they satisfy the other constraints. And what we've done here is just projected them onto the r dot r plane. The red curve corresponds to the projection of the Jacobi energy level on these coordinates, and the blue curve is the H2 is the H2. And when you're in here, H2 is negative. And when you're to the left of this curve here, you're inside the Jacobi surface. So H2 is less than 0 is satisfied inside your Jacobi, and you can see the same thing happens for all these. This is the intersection of the Jacobi energy surface at the boundary of the Hills region about P2. This is the projection for the Hills region about P1. I could, there's more you could say here, but this. The blue is the surface H2 equal to 0. Okay. This gives an idea of what the dynamics is like when you're in these regions. I'll simply look at the case. This is where you're inside the open neck between P1 and P2. In this case, the Hills region he's between C1 and C2. So in this case, Hills region is open at L1, closed at L2. In this case, not all the points satisfy negative Kepler energy. P inside the n minus first cut of the stable manifold means that P transfers after n minus 1 turns about P2 to the P1 region. If you're inside this cut, you do n minus 1 turns about P2, and then you go into the P1 region. If you're outside of the stable manifold cut n minus 1 about T1, then in this case, P stays in the P2 region for at least n turns. These are your stable points. In this case, if the stable manifold n minus first cut intersects r dot equal to 0 at some point r star, then r star is in fact in the weak stability boundary. And this property remains the same even if this is a broken circle, as I described before. You can do this for this range. I'm not going to go into it. This is the range where the Hills region opens on the other side at the point T1. You can do a numerical experiment verifying how this works. Basically, choose a point in the weak stability boundary, and you look at it on the section. Here it is right here. Compute your Jacobi's energy. Compute your Lyapunov orbits, T1 and T2, and your stable manifolds. That is done here. Here is the stable manifold. Here's the let's see here. Here's T2, here is T1. This is your weak stability boundary here. And here's the point we chose on it. Here is your radial line, and you can see how the invariant manifold touches that line right here. So you intersect the stable manifolds with the section which we did. Here it is. And you check that your intersected point is suitably close to the weak stability boundary point, which we have done right down here. And now you want to check to make sure that the point you come up with is and has unstable and stable properties. And it does if you pick the point that we did right here, and you just move very close to it, it's actually a stable point. It goes into the stable manifold. And if you tweak it a little bit, it will escape and it's unstable. So it separates like it should. Here, you can see very clearly, here's a picture of the weak stability boundary. And here you see the points on the unstable manifold lined up on it. And here's a stable manifold, so it lies very nicely on here. There are points which lie on homoclinic orbits, which you can see. I don't want to go into that any further, but there's homoclinic points here. And that's pretty much all I want to say. That's the end of my talk.
Thank you very much.